The role of symmetry in phase transitions.
All right, thanks very much. So what I'm going to do today is to give you an overview of statistical mechanics, its mathematical aspects of statistical mechanics, and particularly phase transitions, and how symmetry affects the transitions and the critical phenomena which I'll describe associated with it. I'm going to try to keep this exposition self-contained and quite non-technical, but if you have some questions, just feel free to ask. And so I will start with the very simplest models of statistical mechanics, which are spins on a lattice. So we imagine we have a d-dimensional lattice which describes a crystal. Or a bar, a magnetic bar, and we're interested, we have spins that are associated with each lattice point in that crystal, and the simplest case is when the spins just take values plus or minus 1. This is called the Ising model, and the symmetry that we'll be talking about in this context will be a Z2 symmetry, and this is one of the most widely studied models in statistical mechanics. So we'll certainly have some things to say about that. In 2 dimensions, as you may know, certain models like this can be solved exactly, and that's the famous Onsager solution. Then the next most complicated one I'll try to describe are what are called Coulomb gases, or XY model. And these are related to a U1 symmetry. So if we make a rotation of all of a simultaneous rotation of all of our spins, then the energy remains unchanged, and that has different behavior from the Ising behavior. So this is a little bit more complicated symmetry group, and then we'll be talking about SO3. But here in this last part, I'm going to jump to. That will be the last part of my talk. I will talk about models which have hyperbolic supersymmetry. So these are like models where the spins take values in the Poincare disk or something like that, and the supersymmetry refers to the fact that they will also have some non-commuting or Grassmann components. So this is related to the reason I'm interested in this, and this is really one of the things I'm most involved in at the moment. This has to do with the spectral theory of random band matrices and random Schrödinger. So we're interested in the eigenfunctions and eigenvalues of matrices like this here. This Laplacian is a finite difference Laplacian on the lattice, and we have a random independent potential that acts diagonally, and we're interested in the spectral behavior of this kind of thing. And there are similar problems for random band matrices, which I'll come to. So these are the kinds of systems that we want to discuss. Now let me just say a little bit more about where the spins lie. So I've already described the plus or minus 1 spins. That usually corresponds to what's called Ising model. They're some of the simplest to define models, but they're not simple, as we'll see. And then if the spin takes values in the circle, so these are going to be all symmetric spaces, and when they take values in symmetric spaces, they're often called lattice sigma models. They take some values in some fixed Riemannian space. They're usually referred to as sigma models. And here this is called the XY model. If it takes values in the sphere, that's usually referred to as the classical Heisenberg model. And now here we go. These last 3 models are again motivated by random matrix theory, random Schrödinger, and here the spin takes values in the hyperbolic plane. This is written as a symmetric space, and here this is a symmetric space augmented with Grassmann variables. This 2 means the 2-dimensional hyperbolic plane, and this extra 2 means I've added 2 degrees of freedom, which are non-commuting variables, and we'll see why that's important to do a little bit later. And this last model is the most complicated of all. This is sort of a simplified version of it, and but this is the model we'd like to understand phase transitions for, but it's quite complicated. This is a matrix-valued spin with a SU11 symmetry, a hyperbolic symmetry, as well as an SU2 symmetry. So this one we only understand partially, even in just one dimension. It's already challenging to understand. So these are where the spins take their values, and they each correspond to different physical systems. So let me just now say how what we do. We associate with a spin configuration. That means a set of spins in a box. So see back here, these J's all belong to some large box in which the spins lie. Eventually, this box will go to infinity. And we will associate an energy to a spin configuration. And basically, this energy really only depends upon what the nearest neighbor spins are doing. And so, roughly speaking, you take the spin at J and at its neighbor, it's adjacent. These are adjacent vertices in my box. And I look at the difference and take some kind of square to get a scalar. And then here I might add an additional term which favors the one direction. And this is what's called a symmetry breaking term, because this term here, which is the main term, this is the one that measures the energy of the configuration and is symmetric. If I rotate all the spins by the same rotation, this energy remains the same. This one breaks the symmetry, but it will be important for later things that I want to say. So we have so far we have a set of spins which are basically elements of some symmetric space, and then we have an energy, and I just want you to notice that this energy has a minimum, which is very easy to describe. The minimum energy configurations are all ordered. In other words, if I want to minimize this energy, this spin and this spin should be identical, so this is 0. And that means that if I'm in a minimum energy configuration, the spins are completely ordered. Okay? Now, what statistical mechanics does, and you'll see this on the next slide, is we look at excitations away from the completely ordered system. And that's what we're ultimately interested in. So we define a probability measure as follows. We exponentiate the energy, e to the beta times this energy. And beta you should think of as being proportional to the inverse temperature. And of course, we have to give a weight for every spin on the lattice. And this is usually the natural measure on the symmetric space. So if we were doing it on the sphere, it would be the usual measure on the sphere. And the Ising model, we just sum over plus or minus 1. So in general, this is a very big integral, an integral in many, many variables. And but this really just acts as a normalization. This is what's called the Gibbs weight. It tells us how to weight our ensemble as a function of temperature and maybe this external field that we have here. And of course, for large beta, or low temperature, low energy configurations are favored, because if this energy is large, then this weight is very, very small. So we're interested only in low energy configurations, roughly speaking. But we'll see that the Gibbs weight changes its character as we vary epsilon and beta, and that's what I would like to describe, how those changes will affect the system. And so that is the sort of mathematical setup, and I will be more specific in a couple of minutes. But right now, let's go to a very precise example. Here is the XY model, and our spins lie on the circle. So you just parameterize it by cosine theta, sine theta. And then our partition function, you just take the nearest neighbor spins, take the dot product of the spins, which is just the cosine of the difference between the angle. Remember, these are adjacent spins. J and J prime are adjacent spins. And here we have something that favors making the thetas equal to 0. It favors making the cosine maximum, which means theta wants to be 0. And this tells us that the angles want to be close to each other if beta is large. So that's our partition function. And our spin-spin correlation is we just define it like this. We look at the spin at 0 and the spin at x, and we weight it with the Gibbs weight. We just put this weight on it, and then we have this normalization factor out here to make sure this is a probability measure. So that's just what statistical mechanics is. I've done this in a box, so this sum and these products range over some finite set of sites, but ultimately we're interested in the infinite volume limit, and that means the box goes to ZD. That's the case that we're most interested in, and this limit actually can be well controlled in this system. You can actually prove that for models like the XY model with suitable boundary condition, this thermodynamic limit, as the box gets bigger and bigger, that means I have an infinite number of variables I'm integrating over, but you can prove that has a nice limit and that this limit is actually monotone as the box. Yeah, I have to have good boundary conditions. If I have funny boundary conditions, then I might not be able to. If I have good boundary conditions, the answer will not depend. Yes, yes. But anyhow, there's certain boundary conditions for which you can actually prove this limit is monotone, which is very nice. So that's a specific example. And now let's see what can happen. What is a phase transition? Well, first of all, let me start out by saying if I drop my magnetic field here, this epsilon, then by symmetry, the average spin will be 0. That's simply because I can flip it and I don't change the energy, so the spin-spin correlation just vanishes. So now I will describe what's called the high temperature or disordered state. And here the spins are random at long distances. That means if I take the dot product of two spins, they're basically unaligned, so this dot product should be about 0 typically, and that's reflected in the fact that this dot product, its expectation is exponentially small for x very large. Okay? So that's what happens, and this L is called the correlation length. It's the length over which the system is ordered, but beyond that length, it becomes disordered. Now, one of the important features which we'll come to, and it's actually one of the central elements of the mathematical theory of phase transitions, is not to prove that this is true. I mean, that's actually not very hard to show, but to understand how this length diverges when you approach the critical temperature, a transition temperature, which is what I call beta critical. And so as my temperature becomes lower and lower, or as beta becomes, as my temperature becomes lower as my beta increases, then my length gets larger and larger and larger, and this is the correlation length, and it diverges, we say, like beta minus beta c to the minus nu power, and this is what's called the correlation length exponent. And we would like to understand how this divergence takes place at the transition, and whether this correlation length exponent is actually universal, which it is expected to be. So this is already one feature. It's a kind of a singularity that's reflected in a phase transition, and this is supposed to be one of the universal features of that transition, which is that the localization, the correlation length exponent diverges with a certain power law. And sometimes this power law can be a log, but in this particular, most of the cases we'll be talking about, this nu is expected to be some fractional number. And so this is conjectured to be universal, and one of the very difficult problems in statistical mechanics is to see to what extent well, sometimes you can calculate it, very special cases, but to what extent is it universal? We'd like to understand, is it truly universal? Yes, Javi.
Is there an intuition why it should be
universal?
System? No, forget universal. Why it should be a power when you know
Yes, well, I'll just have to give you some examples, and the examples that we can calculate, it is a power, and that we know what the power is. Like the Ising model in 2 dimensions, and in high dimensions we know it's a power, we can identify the power. So in other cases, it might not be a power. There's special cases where it might be some exponential. but generically it's a power.
Should nu depend on the symmetric space?
It will very much depend upon the symmetric space. This will depend upon the dimension, it'll depend upon the symmetric space, it'll depend upon the symmetry. Okay? So all these things will very much depend upon all those ingredients, but probably not much more than that.
What's the meaning of nu being universal?
Yeah. What does it mean to be universal? It means that, see, we'll come to that in a second, but basically it means that this exponent here would only depend upon, let's say if I were talking about the Ising model with a Z2 symmetry, and I was in 3 dimensions. Well, I could describe, for example, a quantum field theory, which looks like this. With some coupling constant here. So this is a much more complicated theory, but let's suppose that phi is just a real scalar depending upon x. Now, phi, let's say if it's real valued, then this has a Z2 symmetry. And this has a phase transition in 2 dimensions and in 3 dimensions. And that phase transition would actually be identical to the Ising model. So that's an example. The phase transition would actually have the same, should have the same exponents. And so this is very different from the Ising model because this doesn't take values plus and minus 1. It takes real values. But you can sort of see what the connection might be. If lambda were very large, this field likes to take values plus or minus 1. So it seems to be a little Ising-like, but in fact it's believed, and in certain cases, not this particular one, we can actually prove that this exponent is the same as it is for this one.
So it would mean universal for a certain class.
That's right. Yeah.
With given symmetry.
That's right. So if your symmetry changes, these exponents will change. If your dimension changes, these exponents will change. But I could do other things to the system. I could put in next to nearest neighbor interactions. I could make the field not take values in my symmetric space, but take values in here. So for example, if I were to take this with values in R2, and then this had a U1 symmetry, then I should go back to XY model. Okay? So that's an example of what we mean by universality. And also, by the way, we'll come to this in a second, but when people do experiments on magnets and other systems, lattice gases, they compute these numbers and they compare them to numerical simulations or exact things. And the reason these numbers match so well is presumably universality. These physical systems are much more complicated than these simple ones I'm describing here. So now that's the disordered phase. And the ordered phase is the following. That at low temperatures, the spins are aligned. So they try to look like the ground state. And remember, we said the ground state was, or the lowest excitations were all very much ordered. And so that means if I look at the spin at 0 and x, it will be, let's say, larger than some m squared. That would be like a magnetization in the system. Or it could decay like a slow power law. That can happen too. And we'll see an example of that. Now, here at the very bottom of the screen, I've tried to explain what we mean by symmetry breaking. And the notion of symmetry breaking is quite important. Here I've described everything with epsilon equal to 0. And of course, then the spin has 0 value. But if I first take the thermodynamic limit, and then I let epsilon go to 0, you might think this was 0. But symmetry breaking tells you that if I have an ordered phase, symmetry breaking takes place, which means that I formally have the symmetry as epsilon goes to 0, but actually I don't, because I've done an interchange of limits, and therefore symmetry breaking is associated with this limit as epsilon goes to 0 being positive. So this is very important that I've taken the infinite volume first, and then I've let epsilon go to 0. So that's what's called symmetry breaking, and it's quite an important notion in field theory, statistical mechanics, and many other areas of mathematical physics. So that's what we mean by phase transition. that at high temperature, that means that parameter beta, if you remember, which is the inverse temperature. At high temperature, we'll see disorder. At low temperature, we would like to see order. We won't always see order, but we assume that we will see order. So here's another form of the universality conjecture. Okay. So I'll emphasize it again. Let's compute our partition function with a function of beta and epsilon, and take the log of it, and then divide by the volume, and then let the volume go to infinity. This is called the free energy. This is a very classical, this reflects the thermodynamics of the system as a function of temperature or inverse temperature and epsilon. So roughly speaking, just to reiterate what I was saying before, is that universality means that this is actually, when you have a phase transition, this will be singular, but the singularity, the universality conjecture says the singularity depends only on the symmetry and on the dimension of the lattice. Okay. Now, this requires more stipulations than what I've explained here, but that's a pretty good summary of what we mean by universality. So one thing you have to be careful of is if you have very long-range correlations in your not just nearest neighbor, but you have really super long-range correlations, that will also change the physics. If you have disordered systems, that can potentially also change these singularities. But here you see, if I take a derivative in epsilon or beta, you see a kind of singularity, gamma and alpha. These are the Greek letters that this is what's called specific heat because it depends upon temperature. This is magnetic susceptibility because it depends upon the applied field. So these are supposed to be universal objects again. So I can, if you measure these in experiments, which physicists do, in fact, they even sent some probe up they sent some experiment up on the satellite to measure the specific heat for liquid helium, and so that various gravitational effects could be ignored, just to try to calculate this exponent alpha, and it does agree reasonably well. I think maybe not perfectly, but quite well with the Monte Carlo simulations, which you get from these very simple models. So these are that's the universality conjecture, and it is really the big conjecture in the field, I would say. Now let me go to the Ising in 2 dimensions. This is, as I said, is probably the most well, it's one of the most elegant models in statistical mechanics. It can be solved exactly. At least the partition function can be solved exactly. Your spins, remember, take values just plus or minus 1. We have a Z2 symmetry. We're on the square lattice. And we're interested in long-distance behaviors, always. That's always what we're interested in statistical mechanics. Now, the partition function can actually be computed explicitly. And this was done by Onsager and simplified quite a bit by Kaufman about 5 years later. But you can compute this explicitly. It is the Pfaffian, or you can translate it into a determinant of a Dirac-like matrix. So you can write the matrix down quite explicitly, and you can diagonalize it. And therefore, I can compute its Pfaffian, and I can compute its determinant. And you can compute this expression quite explicitly. This is one of the few problems for which you can do this. You can only do it for epsilon equals 0, no magnetic field. People still work very hard on tries to understand what happens if I have a small magnetic field, but this representation will certainly not work. And in fact, people have tried to solve this model in 3 dimensions. People have gone crazy trying to solve this model in 3 dimensions. It has no such solution, at least to date. At any rate, the spin-spin correlation decays exponentially fast. And here is an explicit value of nu, where I say how this length grows as you approach the critical temperature. And this nu is actually equal to 1. So here's a case where we can actually calculate it. And then you can take perturbations of the Ising model in 2 dimensions. You can add 4 spin interactions and so forth. And as long as they're small enough, you can show that this nu is robust. It doesn't change. The temperatures will change, but this nu will not change. So it's this nu that's universal, not the beta critical. I should really emphasize that point. Now, at the beta critical, the spin-spin correlation has a power law decay. It can't decay exponentially because we're at beta critical. So this quarter was first calculated by T.T. Wu many years ago through Toeplitz determinants, and I think it was one of the reasons that Szego got interested in these Toeplitz determinants. Anyhow, there's a very close connection between Szego's work and this kind of analysis. And at low temperature, of course, we have magnetization. If you're beta, if you're low enough temperature, your spins are ordered, and there is a magnetization in the system. So that's the Ising model. Onsager or others can actually calculate this magnetization explicitly. So this is a very special model. It's very rich. It's still, people are still trying to understand it. And so what is there to understand, you might say? Well, one question is, what happens if this is not zero? And then there's supposed to be some kind of, Zemolodzhikov has predicted some kind of E8 symmetry, this exceptional group symmetry associated with this system. So if epsilon is not zero, that's quite complicated. And the other thing you would like to do is you would like to add disorder to the system, two-dimensional spin glasses, and so forth. And it's still Lefaffian, but then the Dirac operator is not so easy to understand. So I won't go into that. But that's the Ising model in a nutshell. And now if we go to the two-dimensional XY model, now my spins are not plus or minus 1. They lie on the circle. Of course, again, we have this exponential decay of correlations, but the magnetization always vanishes for this system. You never magnetize. Okay? Unlike the previous one where we got a magnetization, this symmetry, because we have a continuous symmetry, the magnetization is always identically zero for all temperatures unless beta is actually equal to infinity or zero temperature. Then, of course, everything's organized. But apart from that, at any positive temperature, you never magnetize. And that's what's called the Merman-Wagner theorem, and it tells you that a continuous symmetry cannot be broken in 2 dimensions. There's nevertheless a transition, which is called the Kosteler-Thouless transition, which is a little bit like maybe the question Avi was asking. You don't have to have order. You can have, in the sense of magnetization, but you can have a very slow power law, which happens at large beta. This is understood for beta large. This is old work that Jörg Fröhlich and I did many years ago, and people have understood much more at a mathematical level about how the spin-spin correlation decays. So it tries to order at long distances, but ultimately it fails because there's a slow power law here. And the conjecture is that at beta critical, the spin-spin correlation will also have this x to the quarter type behavior. So this is very much in the realm of conjecture. And this is basically Fourier analysis in this O2 model, which you have to do. So let me just say a word about that. The XY model is dual to a Coulomb gas. And so let me try to explain that. You see, in the XY model, we have a spin configuration which might look something like this. So these are all unit vectors, but we can have configurations of this type and maybe one with another orientation. And we think of these as being, let's see, I have this one. This one I want to have going the other way. So these are vortex, anti-vortex configurations, and they have logarithmic energy, so you can compute the energy of such special configurations. And you can think of this as being a charge, let's say a +1 charge here, and a -1 charge here. So there's a duality that takes you from basically these kinds of spin configurations into singular vortex configurations. So charges amount to vortices. And at low temperature, what happens is these two vortices tend to bind to each other because plus and minus charges tend to attract. And that gives you the low temperature phase. You get neutral dipoles, which turn out to be irrelevant. And at high temperature, you get a plasma of free charges. And you can think of these as being topological defects in your system, and they run freely. And once they do, it changes the character of the theory, and you get a finite localization. So this is the high temperature phase of the theory. So this is the dual representation for the XY model. And there's been some recent work by Falco, who was here last year, that really describes what happens at the transition for this model. So this is something that you can do. There's some, I think, very significant progress using renormalization group ideas, which I won't have time to explain here. But that's certainly one of the new developments in the field. So now let's talk about the Heisenberg model. So this is, again, two-dimensional, and it is a conjecture, beautiful conjecture, made by Polyakov. And it's like the Ising model, except my spins are on the sphere, on the two-sphere. And the Polyakov conjecture says that for this model, there's no phase transition. It always decays exponentially fast. So you don't have a magnetization, and you don't have a power law. You always have exponential decay. And this is related to the curvature of the sphere, the fact that it has a positive curvature. And so this is one of the conjectures I think many people in mathematical physics would love to be able to prove. It's still quite open, as far as I know. And, but notice that as beta gets large, your temperature gets low, the length over which this thing is ordered is huge. It's exponential in beta. So it tries to order, but it doesn't. Eventually, it decays exponentially fast. So this is quite an important conjecture. And let me just remark that it is related to the following conjecture, which I will try to explain. So as I said, we will quickly be going over to questions like random Schrödinger. So for random Schrödinger, we have a Hamiltonian. So let's talk about it in 2D. You have a Hamiltonian, which is minus Laplacian, which is my finite difference Laplacian. And then we have some coupling constant Vj. So this is random. These are independent random variables. They act diagonally. Now, if lambda is equal to 0, we know what the eigenstates of this look like. They're just plane waves. But when I put lambda positive, so let me just assume that lambda is not 0, but it doesn't really matter. I'll just make it positive. Then the conjecture is, which is very closely connected to this Polyakov conjecture, the conjecture is that all eigenstates look like this. J minus some center divided by L, and L is exponentially large. That's very hard to see on the computer, because if lambda is like a fifth or a tenth, this is a huge scale. You cannot see this on the computer. Okay? You may observe it in the lab, but you're not going to see it in the computer. So these lengths are enormous, but they do have some important physical interpretation. So here I've said it again. But so this fact that you have some non-abelian structure here is related to the idea that the eigenstates are completely different at long, long distances from the way they look in the case where lambda is equal to 0. And this is what's called the localization length rather than the correlation length, but you can see they're essentially the same kind of thing. Now, I would like to remark that if you add topological terms, which measure pi2 of S2 configurations, then they will invalidate this conjecture. You will not get this exponential decay. You'll get something quite different. And so topological defects play a big role in this. Yes.
How do you measure distances on the sphere? So you took linear products for the
Yeah, it's just the dot product in R3. I would take the dot product.
And then
It's rotationally invariant, of course.
so distances are never more than 1.
No, these J's are always nearest neighbor on the lattice, right?
No, I mean, but then when you
Yes.
L, the length L is
No, L can be huge, of course, because it tells you. See, you look at the spin here, and you look at the spin far away, and I want to know whether they're ordered or not, right?
Yeah.
So I'm saying they really will be ordered until they get to a length L, which is this big, and then they will start to disorder because this will be very small.
But the length is on the sphere. So
No, sorry. This, I'm sorry. This X lies in my lattice. It's on Z2.
okay.
Yeah. So I'm looking, see, these are all, these J's all run over the spins lie in the sphere, but the J's and the X's lie on my lattice, just as they did for the Ising and the XY. So we're always looking at very long distance behavior where the spins take value, well, here they take value in some compact space. Okay, so that's what's called the Heisenberg model. So you can see how symmetry is affecting the long distance behavior of these systems in a fairly dramatic way.
I was wondering, you said maybe some physical examples of where these models actually occur in nature?
Yeah, oh, there are, yes, absolutely. So for example, the O2 model is related to what's called the lambda transition in superfluid helium. This one, the Heisenberg model, is, we'll see, is also related to physical systems in quantum spin systems, but it's also very closely connected to this model, to random matrix models. So we'll see that in a little bit, maybe. Yeah?
Is there anything for a triangular lattice?
You can look at this on a triangular lattice, and many of these phenomena will also hold there. Nearest neighbor, yeah, you'll still get the same physics. It's only at zero temperature where things can be different on the triangular lattice. But for these things, for the models I'm discussing, it wouldn't matter whether I had a honeycomb lattice or a triangular lattice or whatever. I'll get the same physics. I'll get the same behavior at long distances. Okay. So, all right. Now let's see what happens in 3 dimensions. So in 3 dimensions, we always have a transition. So here we just saw we didn't really have a transition. At least that's the Polyakov conjecture. But we can prove that if you go to 3 dimensions, you do have a transition. And the transition tells you that the spins at long distances, x is very big, is ordered. So this is like having a magnet at low temperatures. But then when I heat it up, I lose my magnetic moment because the spins are all disoriented. So here I have an ordered phase corresponding to low temperature and some magnetization. And here, when I heat it up, that means beta small, high temperature. I've lost my magnetization. I've lost the coherence of my spins in my system. And so that's the essence of the, so I've gone to 3 dimensions to explain it, but that's the essence of why magnets work. It's a coherent, it's a collective behavior. Now there's a continuous symmetry here, which is broken, just as there was before. But in the other directions, you have a slow power law decay. And this has to do with a continuous symmetry that you have this kind of slow power law decay. So this is actually called a Goldstone or diffusive mode. It's a fairly easy corollary of symmetry and the presence of magnetization. It won't happen in the high temperature phase because there's no magnetization there. But once you have magnetization, the other components of the spin have very slow kind of precession. And that's what this is representing. Now what?
Can you go back?
Yeah, sure.
We have these two things. One is your statistical physics problem.
Right.
The other one is your random sharding.
Right.
And you seem to be now saying the one.
Yeah, this diffusive mode.
Formal.
Yeah, no, it's formal, but you'll see this. I'm going to come back to it. This diffusive mode will have to do with what's called quantum diffusion in this problem.
What I'm asking is there can you take the one problem and translate it to the other?
No, because you had to put supersymmetry into the system. That's the problem. Otherwise, they're fairly close. They're phenomenologically extremely close. But you have to have Grassmann variables. And so far, I haven't talked about any Grassmann components. Yeah. So now you can ask what happens at beta critical in 3 dimensions for these models. And the answer is it's too hard for us to say. We'd like to understand beta critical in 3 dimensions, but we don't have Onsager to help us out. And the renormalization group doesn't do us that much good. Now what Ken Wilson did was he did a 4 minus epsilon expansion and got some information about this. but mathematically we have very, very little information about what happens. We understand these phases, ordered and disordered, but their transitions remains very much a very hard problem. And the real problem there is we probably can never compute exponents exactly, but we'd like to know they're universal still. Okay, now what about high dimensions? High dimensions, everything becomes easy again. So, we talk about 2 dimensions. 3 dimensions is the hardest. 2 dimensions sometimes you can solve. But high dimensions, for Ising and XY models, are easy. So intuitively, what's the idea? Intuitively, if I'm in 5 dimensions, and for example, suppose I look at a self-avoiding walk. Now, that's not an Ising model, but it is not so different from it in some ways. So if I look at a self-avoiding walk in 5 dimensions, it will look like a random walk. In other words, the fact that I have self-repulsion in high dimension, if I take 2 Brownian paths in high dimension, they don't cross. So there's very little interaction in the system. So it's known that the self-avoiding walk looks like random walk in high dimensions, in 5 dimensions or above. It's also known that the Ising model has Gaussian correlations at long distances. So that means if I look at a 4-spin interaction, it factors into pairs, products of pairs with these 2 permutations. And that occurs if J, K, and L are all far apart. So that's what happens at beta critical, so that 4-point functions become equivalent to products of pair correlations, and pair correlations can be computed. So everything becomes much, much simpler in higher dimensions, strangely enough, at least in these models. In the next models I'll talk about, they don't become any simpler, but these are the models for which. So these are classical statistical mechanics models that I've described. And now I will very quickly go to the hyperbolic ones. Okay, so these are hyperbolic ones, and then sometimes hyperbolic with supersymmetry, and so these models, the spin. So before we had our spin. Our spin Sj for j in some d-dimensional lattice would take values. Now we want it to take values. For example, we want to take values in H2, which is the hyperbolic plane, and the energy will be computed with respect to the metric in the hyperbolic target, and then but then a little later I will add. I will add 2. Grassmann or non-commuting variables. And then this will be start to get closer to the models of random matrices and random Schrodinger I described here. But the full model is more complicated still than this, and that's this one with a symmetry group, which is SU1, which is hyperbolic metric. But then these anti-commuting components, they have an SU2 symmetry, and they're all mixed in a fairly complicated way. And I will call this the Efetov model. So this is the one we'd like to understand, but we really only understand something about it in 1 dimension. So I will now try to say a little bit more about this. So what is our goal? Our goal is to understand eigenstates and the time evolution for random Schrodinger and random band matrices. So as I tried to show you over here, when you add disorder or you add randomness, the nature of the spectral structure of these matrices changes dramatically. And maybe I should say the following thing, which is that if you think about the problem classically as a dynamical system in a random environment, so let me say something about that. So you have some perhaps it's useful to give you some classical intuition about what happens, and so I'll try to do that. Suppose I have a bunch of scatterers I'll put them in the plane because that's where I can draw them, and they're randomly placed, and you can think of them as being little bumps in your metric or lattice, and I send a particle, and it starts to get scattered away from here. And you might imagine this is a light ray being deflected by little dust particles, perhaps, in your system. And so you can see that after a long time, this path is not going to go in a straight line asymptotically. And you should intuitively think that if this is the position at time 0 of my classical particle, and I wait for a long time, and here it is at time x of t, well, from this picture, you might want to guess that x of 0 minus x of t, the displacement squared should go like t, like a random walk does. If I have a random walk after t steps, it goes a distance square root of t. And that's what this is saying. That's diffusion. That's classical diffusion, but it's very different from what you would ordinarily do. And this problem, by the way, classically is very difficult. If I put a potential in which is random, and I just send my particle off this way, and I ask, do I have a lot of trajectories which behave this way? We don't know. It's much harder. So this is what's called classical diffusion. And it's unknown. And what we're studying is what I consider to be a simpler problem, which is quantum diffusion. Now, for us, it's very important that these scatters are randomly placed. If you place the scatters in a periodic array, then we understand it quantum mechanically rather well. However, in a periodic array, classically, this is still extremely hard unless you have hard spheres. In that case, it was solved by Bunimovich and Sinai. But in general, these problems, I believe, are much harder classically than they are quantum mechanically. But there is a close relation. Now, what I want to tell you here is that these models are actually, by a kind of duality, equivalent to one of these spin models, but where your spins are basically what somebody called spins on steroids. They're basically not plus or minus ones or lying in the circle. They lie in this matrix stuff with all kinds of complex structure. And so now this slide will sort of summarize what we know and what we'd like to know about these models. First of all, if you have a purely hyperbolic spin model, we can prove there's no phase transition. You're always in the low temperature phase. So that's very different from the Heisenberg model, in which your spins take value in the sphere. You're always in the low temperature phase here. And of course, hyperbolic models, if you look at harmonic maps, for example, we know that these are simpler systems than they are when you talk about targets which are negatively curved, positively curved rather. So this is negatively curved, and it's easier to study. And now the supersymmetric one, this one does have a phase transition. This has a phase transition in 3D, and this is recent work that I've done with Zirnbauer and Dissertori. And this is analogous to a transition in which the particle behaves diffusively here, but if these scatterers get to be too dense, the particle gets trapped. And we call that localization. And so we do have a transition for this model, which is like a localization to a diffusion transition. Now, the proof for the real model, which is what I call the Efetov model, this model up here, this is still wide open. We don't know how to do that. Now, of course, you should probably be wondering, why should I ever see hyperbolic symmetry, and what could it possibly have to do with random matrices? So that's what I would like to explain in the next slide. Okay, so I need 2 slides to explain it. The first thing is, just imagine I have a matrix, and you can think of the matrix as being a finite dimensional matrix if you like. It really doesn't matter. But assume it has random elements in it. And assume the elements are Gaussian. It's useful to have a Gaussian distribution for some of these things. And now I want to understand the spectral structure of this matrix. So to do that, as you may know, the best thing to do if you want to understand eigenvectors or eigenvalues near E, I should look at the Green's function. That means I take the inverse of this matrix around E, I add an I epsilon because I need to do that, otherwise this is maybe ill-defined. And then I look at the matrix element, a JK matrix element, so that's just the Green's function. I take the modulus of this thing squared, and then this average represents the average over the randomness. So I'm just taking an inverse of the matrix, I look at its matrix elements, I square it because that's what you do to calculate probabilities, and then you take the average over the randomness in the system. Okay? That's what we have to do, and that's what I will call script G. It's a fairly complicated, this is a fairly complicated guide to analyze, to compute. If we knew how to compute this for random matrices, we would know much more than we do today. In general, this is an extremely difficult object to calculate. So now, what is quantum diffusion? Well, if I compute this object, and I see that it behaves like the Green's function of a Laplacian, and this is like the diffusion constant, and it decays like this, then that is what we call quantum diffusion, and it corresponds to classically having this particle being bounced around and diffusing like a random walk. So that's what I would call quantum diffusion. And this corresponds to eigenstates which are actually spread out over the whole volume of the system. So psi j squared should look like 1 over volume. So when I sum over the volume, I get 1. And that's what the eigenstates corresponding to quantum diffusion should look like. On the other hand, localization or insulation, which means that these particles are trapped, will have an exponential decay associated with them. So this is like the high temperature, and this is like the low temperature. This is like the symmetry breaking phase of a continuous symmetry. And here the eigenstates decay exponentially fast, and you do not get conduction. So this phenomenon, by the way, was first discovered by Phil Anderson in the mid-50s, and it's called the Anderson transition. And people still study it to try to understand not so much does this occur or does this occur, but how does the transition between these two phenomena occur? And we really don't know. I mean, even in high dimension, we don't understand this the way we should. So now what I've tried to show you here is that you still don't maybe see the connection with statistical mechanics, although the phenomenology seems to be the same. So now I want to describe in the next slide, which is really the key one, why statistical mechanics is helpful to understand such a Green's function. Now, what you may laugh, but the thing I'm going to do next is I'm going to describe what happens when H is a 1-by-1 matrix. Okay? Just a 1-by-1 matrix. Okay? You will see a lot. I mean, it will seem like a crazy thing I'm doing, but this is what is done in the general case. So here it is. This is the origins of supersymmetry and hyperbolic symmetry. It's basically all in here in the next slide. So here I have a 1-by-1 matrix, and I'm going to call it H because that's my Hamiltonian. I'm going to give it a Gaussian distribution. I'm going to set E equals 0, and I'm going to, if you go back and look what I have, see that I'm just going to set that E equal to 0 and make this little h. So and then I don't have any matrix elements because it's diagonal, so there's nothing to talk about. And I want to compute this. Well, of course I can compute this. This is one thing we can all compute, but I'm going to compute it a complicated way. So this is what we want to calculate. You can sit down and estimate this pretty well. You'll see it has a divergent behavior. But now here I'm going to write it out in a very strange way, and this is the supersymmetric way. So this H here is a Gaussian random variable, so I've written it out here. This is the average in H. Should divide by 1 over square root of 2 pi or something like that to give me a normalized average. And now, you see I have a square here. So the square has two parts. It has E minus IH. Oops, I don't want that. Can I get rid of that? Yes, I think I can. It's always asking me stuff like this. Okay. All right, so here I'm going to write, there are two copies. There's epsilon as I epsilon minus h and its complex conjugate. If I do this integral, I will get one phase. This is the complex conjugate that appears in the second factor. Okay? So this is just a trivial identity which relates this number to these two numbers. And notice I'm doing these are Gaussian integrals, so I can just compute these, and if I do this, I will get this exact thing. So this number here is the complex conjugate of this one. Notice that I have an I here. So I times I is -1, epsilon is positive. This is a convergent integral, as is this one. So when I compute its complex conjugate, when you do all this integration at the end, you'll see the hyperbolic symmetry, and it comes from the complex conjugation. There it is here. And here's my symmetry breaking term. It's like the epsilon that I wrote down in earlier slides. It breaks the symmetry, and it's important that it be there, because if epsilon weren't there, this would actually be a divergent expression. So what does this show you? It shows you that this is a useful tool for averaging matrices, inverses of matrices. So here's a more general formulation of it, that we have some big matrix down here, and now instead of having one variable, I have many variables that index by my lattice. And then this little piece down here will give me this Green's function, but I also get this determinant. This is a big determinant that I have to deal with. And so I still haven't seen any supersymmetry, but I need to introduce Grassmann variables to make this guy cancel downstairs. This has got to be canceled. So very quickly, we introduce, and you won't see too many of them around because I know most people are uncomfortable with these Grassmann variables, but they're just ways of putting determinants in, that you introduce other variables which are Grassmann variables, and they produce, instead of an inverse determinant, they produce a determinant. And that determinant is the one that cancels this one down here. Okay. And now, if you like, remember up here, we could actually do the average over the h explicitly, and we got this expression. It's no longer quadratic, it's quartic, notice. Well, that's what we'll get in the end. We'll get a quartic expression in the size, and the z's, and the w's, and so we'll get quite a complicated thing, but all the determinants will cancel, and we'll get a partition function which is equal to 1. Okay, so that's really how the supersymmetric systems work. You need to introduce these auxiliary variables, anti-commuting ones, to cancel the denominator. Now I see I'm running out of time, so let me just go right to our main theorem. Well, here's a hyperbolic spin system, and we write it out in spherical coordinates. This is the one with no transition, and so I won't have time to explain that, but you see the interaction is fairly complicated, but it's actually relatively simple to analyze through ideas of convexity. And so that's something we did a while ago. And now here's the supersymmetric hyperbolic model. It has a constraint which is like being on the hyperboloid, but it also has anti-commuting variables. And these are the Grassmann variables that we need. And here we can prove the existence of a transition. We can prove that there's this diffusion, which behaves like this random walk does. And we can also get, for beta small, the localization, which means that the walk is basically trapped and is not able to move throughout the system.
These two problems, one reduces to the other, maybe they're equivalent.
Yes. Well, this is, yeah, so let me clarify.
You
Yeah.
have to then solve one of them.
That's right. Well, I'm solving this one.
Okay.
This is the one that we solve. Okay. This is the one where you can do this hyperbolic sigma model. It is not the Efetov model. Okay. I wish it were, because then we would have much better, stronger results. We have a model which is a simplified version of it, but it exhibits all the features that the Efetov model is supposed to exhibit, all the qualitative features, namely diffusion at low temperature, which corresponds to this kind of situation, and localization at high temperature, or strong disorder when my randomness is very, very big. These guys, this particle will basically get trapped and not go anywhere, and that's what localization means. It means you have pure point spectrum in your operator. So when you go to the random Schrodinger, you'll see that this beta is proportional to the inverse of the coupling constant here. So at low temperature corresponds to weak disorder, and if lambda is very large, then beta is small. That's like high temperature. So these are my closing remarks. You know, you might think, and certainly I thought for many years, that to understand something as simple as random Schrödinger, it would be crazy to do what the physicists do, which is to write this thing as a field theory, right? You write it as a field theory with matrix entries and all that kind of stuff. But it turns out that it really has many advantages, and it took me a long time to appreciate them. The physicists do most detailed calculations they do in this formalism, and we as mathematicians, or I as a mathematician, want to be able to understand them and justify them. And so one of the main problems that we would love to understand, as you probably have heard of, the universality of eigenspacing for random matrices of all different types. And, but the random matrix I'm talking about here will be something like random Schrödinger or random band, and there are no rigorous results for those cases. But here's what we expect. We expect that there's a universal eigenvalue spacing distribution, and these can be understood in this complicated model by just studying the saddle manifold of the action. If you know that the saddle manifold dominates the physics, which is expected to at low temperature, that explains all this universality of eigenvalue spacing, and it explains that different saddle manifolds coming from different symmetry groups will give you different spacings. So there are other features of this supersymmetric model which, if you study them long enough, you start to believe that that there really is this, although it seems like a complicated approach to a simple problem, this problem is not quite as simple as it might appear to be. So I think I'll stop there.